All right, let's start. Okay. Alrighty, so today we're gonna start the next and main topic for this class, which is the inter-process communication. Um, and remember, we in the architecture review, we briefly talk about the inter-process communication. We talk about there are two main ways for processes to talk to each other. What are those two main ways that processes can talk to each other? Right? Remember, in a modern operating system, uh, the processes, they can't communicate with each other directly, right? Because why? Why was that? Because what we just learned, right? So every process has its own virtual memory space. So there's no memory shared between processes. So there's no easy way for them to communicate. So one of the ways for the processes to communicate with each other is to set up a shared piece of memory, right, by the operating system. So that shared memory space, a memory location can be visited by multiple processes. So processes can communicate that way. Or another way for processes to communicate with each other is through what? Through messaging, right? So we talk about a number of them, right? The queue, the pipe, and all those sorts of different messaging mechanisms for processes to communicate. But for this class, from the no, for this topic in operating system context, we would like to talk. We would like to focus on the synchronization problems uh, for between for the in the communication between processes. All right. So so when we have multiple processes accessing uh, the shared piece of data, so there are some issues that can arise. So if we have multiple processes access the shared data concurrently, right? So there could be some concurrency issues, which we did mention briefly in our architecture review. So what are those? What are those issues? So um, now the basic problem there is the race condition, right? We talk about, what is a race condition? We're going to look into that in detail, but here I just want to give you a quick list on what we're gonna be talking about for the synchronization issues in the inter-process communication. So we could have race condition issues. We could have deadlocks. Remember that diagram I showed you guys? Four trucks going through at a same intersection. They all try to go through that intersection. They can all be deadlocked at that intersection, right? Um, so, so the race condition and deadlock. So there are some there are sort of abstract kind of concepts of concurrency issues. So based on those concepts, we have some generalized real world problems with concurrency. So we will be looking at some typical problems there, problems like producers, consumers, right? That problem is essentially a bounded buffer problem. I'm not sure if you guys, learned that concept, saw that problem before. It's essentially a bounded buffer problem. Uh, a typical example is a video audio streaming, right? So in that kind of context, you have a source producing video or audio content uh, that that is being sent to the other end, which is a consumer, to consume the video or audio content. So And the producer, you don't want the source of the video or audio produces more than what the consumer can consume, right? In that, in that case, you will have an overproduce problem. And in the bonded buffer context, you would have a over buffer flow, a buffer overflow kind of problem there. Or if your consumer is consuming the video or audio content faster than the source can be producing, then you would have a buffer underflow problem there. So, so that's a typical example there for producer-consumer problem. And we also could have a typical problem that we can generalize as writers problem, right? So you could have, you know, a banking system. So you could have multiple ATMs, like the same account holder can access the his or her account uh, at the same time, right? But all of like this user can read like can access his or her information, banking information, but there can only be uh, one process there that can update the account balance there. So so that's what we can generalize as a writer's problem. Now there is also a typical scenario for deadlock problem. It's what we call dining philosophers problem. We will look into that later on. So this is just a quick summary that the concurrency issues that that you can run into in a multiple process environment accessing shared data. All right, so what are some ways that you can use to handle the concurrency issues like the race conditions, the deadlocks? Now, over the time, people developed certain programming constructs that we can use for handling these concurrency conditions. Constructs like logs, semaphores, monitors, we'll get into those in greater detail later on. So, all right, so let's look at a basic problem. So for us to understand, you know, what a race condition is. So so we have like two pieces of two sequences of programs, P1 and P2, right? So these two, let's call, you know, two processes. So these two processes, they all want to access a shared variable in this integer x, okay? And also, they also want to access a shared location in the memory, right? It's 0x3000. 3000. Sorry, let me grab my pen here. So, right, so what we call these two like resources, what we call here in this context, they're shared resources between P1 and P2, right? So, you know, P1 and P2, they're very simple sequence of instructions. So P1 is doing X++, right? It's trying to increment X, and P2 is trying to decrement X. So now, what we learned from the CPU scheduling, right, from what we learned there, is that these two processes, during the execution of these two processes, you could have what? In the middle of executing either process here, the process could be what? Could be suspended or could be switched out, right? To have another process put on the CPU for execution, right? So we cannot. So you could like for P1, the P1 could be switched out here, right? It could also be switched out here, right? The same thing applies for P2, right? So with that kind of possibility, so what do you guys think? Like what kind of a result you could get after P1 and P2 getting executed? What kind of possibilities you could have? Anybody? Let me bring up the chat window. You can type your answer. See, I don't, it's weird. I just can't see my chat window while in the PowerPoint mode. So who can give me like a possibility or a few possibilities of the result that the like after executing P2, P1 and P2, what could be possible outcome from the execution of P1 and P2?
When you're trying to increment, P2 can like grab it and decrement it, and then so now P1 has like an old copy of the value, so then it's just it is the same instead of both happening or something.
Yeah, great. That's definitely a possibility. Yeah. What about other possibilities? So just tell me what kind of possible values X can have after P1 and P2 getting executed. Right? So
someone said -1, 0, and 1 in the chat.
oh, okay. Yeah, that's perfect answer. Okay, great. Yeah, so it's like, yeah, so here with this with the context switch I just talked about, right? So the execution of all these instructions, they can interleave with each other, right? What would be the best scenario you expect? You right? The best scenario is what? You would probably expect this whole P1 would be executed first. Then you move on to P2, right? Right? Or you would want to execute P2 first, then execute P1, right? So basically, essentially, you sort of want what? You sort of want all the instructions in P1 can be what? Can be executed all together at once, right? Without being interrupted by P2, right? Suppose you only have two processes in the system, right? So that's basically what people normally would expect from, when you design these two pieces of programs, right? Normally you would expect that would be the case, right? But again, in a multi-programming environment with context switch, the outcome of executing these two programs is what? Is unpredictable, okay? All right, so I just mentioned that, what you expect here, you want this whole piece of P1 to be executed without being interrupted. What does that mean? Do you guys know a term? That if you have a set of instructions, oh, Frankie raised hand, okay. My apology. Oh yeah, I saw the chat window now. So who can give me that term that like a set of instructions, you want to execute a set of instructions. You want to make sure the execution of that set of instructions is not interrupted. What do you call that? Do you guys know that term?
Can you just put it to sleep? Like make it sleep a certain amount of time and then have the process wake up?
Is it a critical section?
That's an interesting idea. What did you say, Amy?
Is it a critical section?
A critical section, yes. We will get into that, a critical section. But what I'm talking here is that if, say we have a set of instructions here, P1 or P2, if we want to execute this whole section, right, of instruction for either P1 or P2 without being interrupted, what do you call that? Oops. Have you guys heard about atomic operation? Yeah? Yes or no? That's important. That's important for me to know. Do you guys know what is an atomic operation? What does that mean? Nobody knows? So what the definition of an atomic operation is, you look at here, x plus plus. Normally you would think x plus plus is what? It's just a single instruction, right? It should be executed without being interrupted, right? But it turned out most of the implementations for that simple thing, x plus plus, you need to do 3 steps here, right? So if you can achieve executing these 3 instructions without being interrupted, then you can call that operation as atomic operation. So that's what we mean atomic operation. Atomic operation means once you start the execution of that piece of program, it cannot be interrupted or stopped or suspended during its execution, okay, until its completion. So that's what we call atomic. All right, so, but that's normally what you expect, right? But in reality, this x plus plus actually, it can be interrupted, right? So how do we guarantee that this cannot be interrupted? And we can discuss about possibilities later on. So, sorry, somebody has a question here. All right. So that's an important concept there. So, but let's say, you can't guarantee, right, this execution is atomic. You can have, during the execution, this process, either process can be switched out for other process, to give CPU to other process. So how do we guarantee, like, we can get the outcome for what we want for executing these 2 programs, right? So basically, we need to ensure the order of the execution for P1 and P2 is what we want, right? So that's sort of what we need to solve for this. So, but here, this scenario describes a typical race condition. Okay. So basically, a race condition is that you can't really predict what will happen, since the result depends on which one goes faster here, P1 and P2, right? For each instruction here, right? And what happens if both of these programs, they go at exactly the same speed, right? So, so we need to find a way to ensure the order of execution between these 2 programs. It would be the order that for what we expect or what we want, okay? All right, so yeah, so this is what I just talked about. So now the race condition here, I need to stress an important thing here about all the synchronization problems, including the race conditions, the deadlocks. There are problems, not that they are bound to happen. Okay, so for the programs we just talked about, these 2 P1, P2, it's not that they will definitely result in race condition, right? So it means there is a possibility that the execution of these two pieces of programs could like interleave with each other, right? Could interrupt with each other. There is a possibility, okay? It's not that it's gonna definitely happen, okay? So, but if there is a possibility, then there could be a problem, right? So when we talk about race condition, deadlock later on, so these problems, these synchronization problems, if they have a chance to happen, then we call there is a problem, okay? People get what I'm saying? All right. So obviously, in most situations, race conditions are definitely not acceptable, right? So it could, again, it could lead to unpredictable results from the execution. And more importantly, it could lead to what? Compromised data integrity in your program, right? In a piece of program, we just saw that variable X, the value of X is the data there could be compromised, right? The data integrity could be broken there. So, all right. So what we need to find is the solution would be we need to find ways to ensure the order of execution is there, right? All right. So basically, you can say most of the synchronization problems, they are what? You have multiple processes or multiple threads, they're trying to access a piece of shared data, right? They all could be trying to update that piece of data. And if that happens, then you could have problems. All right. All right. So, all right. This is what Amy just mentioned: critical sections. So, um, so how do we handle the race condition, right? So, so basically, there is, so it's essentially the way is when you access that piece of shared data, when a process accesses that shared piece of data, the portion of that program needs to be what? Needs to be guarded or protected, right? So that means that section, what we call critical section, is that you cannot have multiple processes accessing the section at the same time. Now, here we need to make sure we understand the critical sections. They are not necessarily the same among all the processes. So basically, as long as you're accessing some shared data, right? You need to protect that shared data to be accessed by other processes, to be accessed by other processes. So, so that's what we mean critical section. Now, so basically, what we need to implement here for the critical section, it normally has three pieces of code for a critical section. So when a process tries to enter a critical section, it needs to request for access. That's what we call entry, it tries to negotiate to enter the critical section, which has some shared data access inside that critical section, right? And that the access to the shared data there has to be what mutually exclusive among all the processes. Right? So after you gain the access to the critical section, then the process will execute the critical section, and when it leaves, it will release the lock on that critical section. So so basically, when you enter the critical section, you are sort of has has a piece of a lock, what we call lock. Later on, we will discuss about that in detail. So you will have some sort of access granted to this process. Then you can access the critical section. And after you exercise your code in the critical section, you're going to release that lock so that other processes can grab that lock, and so that they can enter their corresponding critical sections, which include the same shared data. All right, so so as I just talked about, so you can divide the critical section into 3 pieces: the entry, the critical section itself, and exit. And the remainder would be all the code that doesn't involve the shared data. Okay, so the critical section is essentially basically the section that accesses the shared data. Okay, so the remainder would be not accessing the shared data. All right. So any questions about the how we divide a program based on critical section? All right. So again, a critical section is a sequence of instructions that can be executed by at most one process at the same time. Okay. So we can break the whole program into 4 sort of sections. Okay. All right. So here we have a quick kind of implementation for solving the problem, the race condition we just had, we just looked into. So we have the same 2 pieces of programs here, P1, P2, they share the data X, right? So one is trying to increase X, one is trying to decrement X. So both of them, when they try to access the shared data in X, they're trying to what? To request for access first, right? And once it has the access to the critical section, so here the critical section is what? It's just this one piece of code here, right? So once it enters the critical section, it can just change the data there, all right? Once it is done with the shared data in the critical section, and it leaves the critical section, and the exit here would release whatever the log the P1 has gained access to that critical section, so that P2 can grab that log and execute. Or so basically with the critical section here, you can ensure the order of execution, right? Either P1 gets executed first, or P2 gets executed first, right? And you can ensure the code in the critical section to be whatever the code there to be executed, not to be interrupted by either processes, right? So, but now an important thing I want to mention here, while the P1 is being executed here, oops. I want to ask if P1 can still be switched out, like can operating system still, during the execution of P1 here, with this critical section kind of protection, can in the middle of executing this piece of program, okay, can P1 still be switched out for another process execution? Who can answer that? Hello?
Wouldn't you have to wait either way? So no?
No? So you're saying this is atomic section? So that means you could, with this critical section, that means with this critical section guarding this piece of program, that means this piece of program becomes atomic, that they cannot be interrupted.
Yeah, right.
All right. Yeah. Well, that's That, I mean, you would normally think that would be the case, right? But remember, so critical section. Okay, just remember this. Critical section is not necessarily atomic. All right. So here, in the middle of execution, for this P1 here, the execution here, say P1 enters the critical section right here. Right before it executes X++, it can still be switched out, okay? Okay, there is no control there, okay? But if that's the case, that's the case, then but we still have a problem with the shared data X here. Can we still have a problem that can X, even P1 is switched out, okay? Right before, or remember like X++, right? X++ has 3 steps, right? We just talked about, we just saw that, 3 instructions, right? During the middle of execution there, it gets switched out, right? But can P2 mess up with X while
No.
P1 is switched out?
No,
No. Why? Why is that?
because of the entry and the exit. P1 hasn't exited.
Right. Yeah.
So it's like
So
protecting memory.
absolutely. Yes. So great. So basically, so even P1 gets switched out during the execution of this piece of program. Say P2 gets put on CPU for execution. But since P2 doesn't have what? Doesn't have the access here, right? P2 will be blocked, right? Will be blocked at the entry of the critical section. So P2 has no chance to access X, okay, to do any change there. Okay, so essentially, so again, this is a very important, this is critical that we understand that the critical section is for what? For protecting the access to the shared data. Okay, it doesn't mean the critical section itself is atomic. Okay, it just even during the middle of executing that critical section, the process gets switched out. Other processes, they won't be able to access the shared data protected in that critical section. Okay, so that's so the critical section is providing what is it is providing the mutual exclusion for accessing the shared data. Everybody clear about that?
Yeah. Could
Okay.
you give some examples on what type of things would be atomic?
Yes, we will get into that actually. So for implementing, we'll get into that when we implement critical section, right? So then we need some hardware or architecture support for some atomic operations for us to use to actually implement critical sections. So I will get into that. All right. So but that's definitely a very, very good question. So, all right. So everybody understand what I just said? That's very important, okay? It's not that the critical section it's there for providing mutual exclusive access to the shared data, okay? It doesn't necessarily mean the critical section itself is atomic, all right? Okay. So, all right, so here are some definitions of for critical section. So essentially, we need to have 3 conditions for a critical section or region. So the first one is mutual, it provides mutual exclusion. No more than one process can access the shared data in the critical section, okay? So you have multiple processes, they can have different critical sections, okay? But they can be mutually exclusive to each other because of what? Because they are all accessing the same shared data, okay? It's not that you have to have critical section the same among all these processes, okay? All right, so, and also a critical section needs to also have two other properties, which are also very important we need to discuss here. So it needs to ensure a progress property. So that means if no process is accessing the shared data, and you have multiple processes are trying to gain the access to their respective critical sections to access the shared data, then the critical section needs to ensure one of the process will gain access, right? So it's sort of that if you don't have any process accessing the shared data, and you at that moment you have multiple processes wanting to access the shared data, right? So eventually the critical section has to allow one process to enter that critical section, right? To access the data. That's what it means here. All right. So what are the processes that get to participate in deciding which process to enter the critical section in this for this scenario? Okay, so if you don't have any process accessing the shared data, so basically that means all processes that requested the access to the shared data or are waiting for entering their critical sections, those processes, they need to be allowed to participate, right, in the decision to enter the critical section, right? So that's sort of the first group of processes. And also, this process that is accessing the shared data at this moment, that process, if that process is exiting the critical section, that process also gets to participate to decide which would be the next process to enter the shared data, to enter the critical section, to access the shared data. All right, that's what it means here. Okay, this is from textbook, but I want to explain what that means. Everybody getting the idea of what I'm talking about? Right? So this is sort of like, I mean, abstract, but you have to understand. So the critical section needs to ensure that progress is there, right? 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 So if no process is accessing the shared data, that means what? That means you don't have the actual critical section being executed at the moment. So that means that the process just access the critical section for that shared data. That process is exiting, right? So that process and all the processes requested wanting to access the shared data in their critical sections. So all these processes, they get to participate to decide which process is the next one to enter the critical section. People get the idea? Okay, so that's what it meant here. Okay, and the bounded waiting, what is bounded waiting here? So it's sort of like, so so again, the critical section is guarded, right? So only one process can enter its critical section, right? So you can have multiple processes requesting to enter their critical sections. but one of them can actually get into the critical section, right? So after, say you have a process, accessing the critical section, and then after that process finishes with the access to that shared data, it exits. Okay, and we need to have a mechanism so that all the processes that are waiting, they don't wait forever. Okay, that's essentially what this bounded waiting means. Okay, so say I have I'm trying to make my pen work here. So I have A, B, C here. Okay, so while A is accessing the critical section of the shared data, it never works on the PowerPoint. So while A is executing, B and C, let's say B and C, they both requested the access. Okay, they both have requested the access. They're waiting, right? All right, so they're waiting. So after A finishes accessing the critical section, either B or C will be picked, right? Right? For the next to access their critical section, right? So the bounded, but here I only have B and C. I only have two, but you could have like how many? You can have a long list of processes waiting for access. For gaining the access to the critical section, right? So the bounded waiting is making sure from the time each process requested the access to the critical section, eventually, every one of these processes will have the access, will eventually gain the access to the critical section. You guys got that? Is this part confusing?
How do you determine that though? Is it like, are they in the queue, or do you put them all to sleep and then whichever one is like wakes up?
That's an excellent, yeah, that's an excellent point, Frankie. So that's actually one of the ways, right? You could put all the waiting, so all these waiting processes into a queue, like a FIFO, right? We always come back to our good friend FIFO. All right, so you could have a FIFO queue there, right? Depending on depending on the time each process requested the access, you can have a FIFO queue, right? You can just pick the process from that queue, right, to give the access, right, for each process to enter the critical section, or you can set up some sort of priority, right, mechanism to allow the higher priority processes to enter the critical section. But in that case, you could end up with starvation for certain processes, right? So it's sort of similar to CPU scheduling. So basically, it's sort of you have the critical section is like a CPU, right? So every process wants to gain access to it, right? So yes. So what I'm here trying to describe is that the critical section needs to have this property that for all the processes waiting for gaining the access to the critical section, they will not wait there forever. That's what we call bounded waiting. Okay. Now the particular wording here I put on the PowerPoint for bounded waiting, that's from textbook, but that's sort of hard to understand. So what I'm trying to do is trying to explain what that means. Okay. But very good point, Frankie. All right. So all right. So how do we this comes to what Amy just asked. So how do we implement critical sections? So, so one thing is we need to know, one thing is we need to know what is a critical section. We just talk about it and how to apply that to the shared data access issues, right, among multiple processes or multiple threads. The other thing is, for the purpose of learning in this course, we need to look into how the critical section itself is actually implemented, right? So can we achieve the critical section on the software level only? Can we only use software to achieve critical section? Or can we achieve the critical section with a combination of software and hardware support, right? So next we're going to talk about a few options we have. Basically, we need some hardware support, and the atomic operation comes to the picture, okay? All right, so when we talk about race condition, right, we just talk about it. We talk about the execution of your program can be suspended at any moment, meaning it can be context switched out for another process to be executed. So on a single processor system, a simplest solution is we can do is we can disable all the interrupts, right? So while your process is being executed, we can disable all the interrupts, whether the interrupts are from the software level or from the hardware level. We could disable all of them, right? So your process can execute a set of instructions, the critical section, without being interrupted. That's definitely, that's sort of one option there, right? So without interrupts, with interrupts disabled, the CPU, we talk about, the context switch is based on a clock, right? A clock interrupts, right? So the CPU will not switch from your process to another process, right? So there will not be any context switch if you disable all the interrupts there, right? So that's one way, right? But this approach is generally unattractive, right? Why is that? Because it is unwise to give the user process the power to turn off the interrupts, right? So we go back to the privileged instruction execution. So if you give this authorization to a user process to turn off the interrupts, bad things can happen, right? So what if it turns off the interrupt and it just occupies the CPU for its own execution forever, right? So, and also this disabling the interrupt only sort of is only applicable to one CPU for uniprocessor environment. But if you have multiple processors in your environment, what are you going to do, right? So that's one option, but definitely not a realistic or practical option, right? So that's one way. But that's one way from the hardware level. But let's look at a few options from software level. Okay, so let's look into these two options here to see if any one of them can work. Right? These are all purely from software level. Okay, so let's look at the example from the left, the right side first, the full bar. Okay, right? So it tries to do what? It tries to set a shared variable, a locked variable, right? So while the locked is there, is true, it means some other processes already entered another process already entered the critical section, so you can't really do anything, right? So you will just what? You will do some kind of wait here, right? And once the other process finishes with the critical section, the locked variable will be changed to what? To false, right? And then it will then this can enter its critical section here. But will this work? Will this work? Anybody? On the right side, will this solution work? This is sort of a naive kind of solution here.
I guess, couldn't it work? It just
It could
bad.
work, right? Yeah, a bad in what way, Eric?
You're unnecessarily using resources because you have a while loop sitting there, so it needs to run through the while loop all the time, so it's checking all the time.
That's an excellent point. So here, there is a problem here. So it's what we call busy waiting. Okay, another term is called spin locks. Okay, so this is a problem here. Yeah, so it uses CPU resource, right? Doing this busy waiting, what we call spin locks. Okay, that's one problem. But even with this, that's an undesirable thing, right? With this solution. But will this work? Will this actually protect the access to this critical region? Will this solution work here? What if right after, right after you check this locked, say this locked variable becomes false, right? So then it will break this while loop, right? And then it will right here, say a context switch can still happen right here, right? You can't prevent that from happening, right? A context switch, right, can still happen right after you get right after it gets out the while loop, right? So this whole thing can still be switched out. So while you so you find lock is false, before you set the lock to true. Why do you want to set the lock to true here? Because you want to you want to use this locked variable to protect this critical region, right? Once this locked variable becomes true, all other processes, they can enter the critical section, right? But what if right here, this gets switched out? Then you still have a problem. Right before you set this locked variable to true, you get context switched to another process. So this in general wouldn't work all the time, okay? What about this one? What about this one? Okay, so I won't get into this for because of the time. I guess we need to talk about the quiz one now. So, but anyway, so this would work. This left side solution for protecting the critical region, for protecting the critical section, but it has this problem as Eric just talked about, the spin lock. So it's a busy waiting. So it's basically it's not a desirable solution there. All right. So but more or less if you only do this on the software level, okay, you would end up with some kind of busy waiting, okay, for implementing the critical section. So this is there is this Peterson's two-process solution. He came up with this software only kind of solution for critical section, only for the mutual exclusion, okay, for accessing the data. Okay, so let's see how this works very quickly, then we can stop here. So here, assuming you only have two processes using this program for accessing the critical section. So this whole enter region is what we call, it needs to gain access, right, to the critical section. So here, each process gets assigned with a PID, right? All right. So you could say PID here either 1 or either 0 or 1, right? Right. So and also so this PID gets associated with this turn variable here. So let's say if turn is 0, that means process 0, right, wants to access the critical section. Remember, this enter region is that negotiation, right? A section of the critical section. Okay, so if turn is 0, then that means process 0 wants to access. If turn is 1, that means process 1 wants to access the critical section. Okay, and also there is this simple array here indicating the interest to access the critical section for each process. All right, so whenever a process wants to enter the critical section, it will enter this kind of, it will call this enter region, right, with the process ID, right? So it will check. So let's walk through this very quickly. So let's say we have two processes. None of them is accessing the critical section yet, okay? Then the first process comes in. Let's say process 0, okay? So what's gonna happen? So process 0 comes in, right? It will set its interest to access the critical section here, right? So interested, so here, right? So it will set the, so process 0 will set what? Will set interested 0 as true, right? Right? So then it will also set the turn to the process ID, which is 0, also 0 here. Okay? And then it will come here and it will look at, okay, so yes, turn equals to process, obviously. I just set the process to turn, right? So turn is 0, process is 0. What is this? Interested, the other process, is the other process interested yet? No, right? Right? People following? So that means, okay, so this is false here right now. Okay, so this wouldn't satisfy for this while loop. Okay, so it will what? It will be granted with the access. Right? People are following? Hello? So I can't see any interaction here. So the first process will gain access, okay? And let's say after the first process gain the access, the second process comes in, okay? The second process will do what? Will come here. The second process will come here. It will set what? It will set the process, it will, sorry. So it will set the interested 1 to true, right? This is the second process, right? And it will set the turn to what? To 1, right? And then it will come here. So turn equals to 1 here. Yes, you just set it, right? You just set it to 1, right? Here. And this would be true, but you also have the interested of other. Other is what? Other is the 0, right? The previous process. So that's also true because that process is already in the critical section, right? So the process 1 will wait. will be blocked here. Yes? Only after process 0 finishes with the critical section, then process 0 will exit the region by setting what? By setting the interested flag here to false. Then if once that is set to false, then this will become what? This will become false, right? And then process 1 can gain access. Now, is this hard to follow? I know this part is, we have to go through, we probably don't have time to go through all the scenarios. This is just 2 scenarios. So we also need to talk about who, like, I mean, what if 2 processes, they're trying to enter this, trying to call this at the same time, right? But if you walk through the logic as what I just did, you will find that this does provide mutual exclusion, okay? But this is only for 2 processes. There is a version for multiple processes, okay? We won't cover in this course. And also this solution, it provides mutual exclusion, but it doesn't provide the progress property, the bounded weighting property we just talked about. So this is, in a strict sense, this solution is not satisfying all the properties for critical section access. Okay, so people having trouble following this? Yes? Well, then we will get into that later. All right, so I guess, oh, somebody. Alex, you said about that disabling interrupts. So sure, you can have, what I meant disabling interrupt there. Alex just just posted a comment on what I said about disabling interrupt for accessing the critical section. What I meant there, let's say you could give the user a process the ability to disable all interrupts, including the user level. Well, interrupts essentially it's only on the privilege level, okay, for all the interrupts. So, but again, that's not a realistic solution here. But here, like what we just talked about, this Peterson's 2-process solution, it is working purely by software, but it is also has 2 things. One is the bounded weighting property would not be satisfied for the critical section. And also it also has this busy weighting here, okay? Which is not desirable. Okay. All right, so we'll stop here. Well, I guess we only have 10 minutes left for the class. I guess let me stop the recording. Oh, maybe, you know, when we talk about, we can still record for what we are discussing for quiz 1. So let me share the screen. Share me. Okay. Let's see here. Okay. All right, so for quiz 1, so basically, you know, as I stated in the announcement, we have the quiz 1 with sort of 75 minutes workload. There, what we meant there is that the workload is supposed to be 75 minutes, okay? So you should be able to finish it, you know, by within that time frame. But you do have 16 hours to complete it, right? So from 4 p.m. to 8 p.m. To 8 a.m. next morning.
Are we not having a lecture on Thursday?
No, it will
Okay.
not. Yeah. So good question. So we will. So you can start working on the quiz from 4 p.m. So as far as the difficult level of the quiz, it has been a tough time for everyone nowadays dealing with this, stupid virus thing. So a lot of you, I know a lot of you went through um, a, a whirlwind of events over the last couple of weeks, right? Especially those of you who had to move due to the school shutdown or something. So I'm all for finding the right balance of the difficult level for the quiz. Okay, this is my point. So so you like essentially studying the assignment, the slides, the book will be more than sufficient for this quiz. Okay. So I will be posting the key to assignment 4, the non-programming portion, like tonight. Okay. So again, as I put in the announcement, there will be like, most likely will be 5 problems. Okay. Uh, uh, as I put, like those 5 problems, they're sort of like for each problem, it's a combination of definition and essay questions. So I think for definition, you guys won't have any problem. Just search the book, your notes, the slides, right, the assignment, and I guess you guys should have no problem of those. Yes, Frankie. Yeah, you can just unmute yourself and just talk. Yeah.
Are we gonna have to do like calculations, or it's like the turnaround time and stuff like that, or is this gonna be like mainly like you said, definition and essay type answering?
I can't give you that. I can't tell you that. But if it ever involves any calculation, it would be very simple calculation. Okay.
Okay,
All right.
thank you.
Not even as complex as what you did for the CPU scheduling in the assignment. It's not to that complexity. Okay.
Okay, thank you.
All right. No problem. So but basically, but we for open book exams normally. We give scenarios, right? So you would have to be familiar with all the, it will test your understanding of the important concepts, right? So that we deem important concepts. So, just remember what we stressed about when we talk about those concepts in the class, right? I don't, if you just look at your assignment, you will know the focus, where the focus is. Okay. All right. So and I want, so for the scenarios I just talked about, you will give like a sort of a given scenario that you have to evaluate. It will ask you to make some decisions, based on a given scenario. It will ask you to do to propose a certain design, or 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 or, or ask you for a qualitative answer or quantitative answer. Okay, so as long as you understand the concepts, you shouldn't have any trouble.
For the scenario ones, will there be like one accepted answer, or will you accept different ones based on like justification?
That's a very good question. Yeah. Well, in general, we're making these scenarios pretty. I think you probably. Well, first of all, it wouldn't be open-ended. Okay. So sort of, we will have, like, your answers should be all similar if they're correct answers. Okay. But yes, but justification is very important. This is almost like equally important as your answer. Okay. So if you only give a correct answer without any justification, you will only get half probably points. Okay. So But if you have a very good justification for an incorrect answer, we will still try to give you some points, put that way, you know. So just for, you know, because you're thinking, right? You're thinking based on your understanding of the concepts. All right. So these you can expect why we set up these. If we give you all the, you know, filling the blanks, you know, definitions, it just is no point, right? Doing the open book, right? But as I put in the latest announcement this afternoon, so those. That was from Dr. Roche to her students, and I would say the same to you guys, right? So if you try to do the work by yourself. I mean, not try. Like, I mean, you are required to do the work by yourself, and you would find if you just search your book, the notes, the slides, the assignment, you should have enough information, okay, to answer these questions, okay, and more like it's probably quicker if you do that way, okay, instead of you're trying to search the solution. But one thing I do want to make sure, okay, I do want to make sure you guys all understand. This is very important for me to say. Please do not post your solutions for others to see. Okay, that's basically a big no. Okay, so so if you ever if we ever find that out, you will be in trouble. Okay, so and we will be using the Turnitin submission for the quiz. Okay, because Turnitin can compare all the answers, right? To find like if two answers they're essentially the same, you will detect that. Okay. All right. So and you guys will also, along with your submission of your answers, you will have to do submit that single examinee affidavit. Okay. With your name printed there as your signature. Okay. I know nobody wants to listen to all these rules, but that said, we as instructors are obligated to mention these before the open book test. Okay. So there are a lot of other instructors, professors. They actually they would do the test with. You guys familiar with the lockdown browser? For open exam. So we choose not to do that. Okay, but the thing is that if we ever find out there are indications that people are doing what they're not supposed to do on the quiz, we will consider to use a lockdown browser in the future. So for the sake of yourself and others in the class, please do not do those things, for what I just mentioned. Okay. So, all right. So not really, let's just quickly go through this. So essentially just the quiz will cover two chapters, chapter 1 and chapter 2. One thing I can say is that chapter 2 obviously probably would be tested more. Okay, that I can tell you. So yeah, I'm not sure how I need to go through this list with all you guys, but basically, you need to get familiar with all the, like at least, during the test to have the slides open, right? Have the book, like get familiar with all these sections in the book. At least you know where to find what information and your notes from the class. So again, chapter 1, you can say, we will have some problems from chapter 1, but you can say chapter 2 probably, because chapter 2 is one of the main topics, right, in the class for this course. So you will get more problems, definitely in that chapter. So, so you guys have any questions? Already? So even I give you the quiz today, you guys are all good now?
Will this quiz be an indication of what the other two's going to look like in terms of difficulty and the type of questions?
That's a hard question to answer, but that's a good question, Eric. We don't know, because one concept could be easy to you, it could be difficult to others, right? Even for the basic understanding, right? Let's say, like for the virtual memory paging we just talked about, the last main topic we talk about in the class, paging concept. Some people, they just easy to them to understand, but for some other people, they're having hard time to understand what paging is. So I guess what we can say is that we'll test your basic understanding. Okay, so it's not like we're going to come up with a complex setup. You wouldn't get that. So, but hopefully that answers that. Does that answer your question, Eric?
Yeah.
Yeah. So, yeah. Any other question? I don't know. Actually, I don't know what more I can talk about actually. So, things like you did in the assignment, right? Those are probably more important, right? So, I can say CPU scheduling is important, right? Right. So, what we list essentially, what we list here, oops, here for chapter 2, oops, I'm keeping jump. Okay. So, right, so here, all these, you can say they're all important to me. And you know what's important in chapter 1, right? Just remember what I talked the most in chapter 1. Right, so, and yeah. Any questions? No? Okay, so again, for the submission, okay, turn it in. I don't foresee you guys will have any problem submitting for the quiz, because you will type some answers in your Word document. Then you can convert it. You can either leave it as a Word file, or you can convert it to PDF. Okay, either way. But as long as, if you convert it to PDF, as long as you have some text there, typed text there, that can be recognized by the Turnitin, it will let you submit. Okay, but remember, don't wait until 7:59 in the morning to submit. Okay, so because we will set the time, we'll set the submission not to allow the submission after the due time. Okay, if you wait until 7:55 a.m. to submit, you're with your own luck, So if you can't submit, that means you lost. So, but you should be able to just try to submit, way before that. Okay, you have enough time. All right. Okay, I guess I can end the, let me end the recording.